welcome. You are welcome.
Thank you,
to today's presentation, hands-on on the machine learning using R. Over to you, sir. Dr.
Yeah, good evening, everyone. I welcome you once again. Those that have been joining us since the beginning, and for those who are just joining us, you are welcome. Well, we'll be going through a journey and machine learning. And I believe it's something that one or two persons have been looking forward to seeing. And it's not new on this platform because the last facilitator, Dr. Ekum, actually introduced the concept of machine learning to us. And we taught how to conduct the train and the testing procedure. We're put through all that. So this morning, this evening, we are still going to travel that route, and we are going to be laying some foundation. I hope I can share my screen. Doctor, okay?
Yes, should be able to share.
I'm trying to, okay. Which one am I sharing? Okay, this one. Share. Is it showing now?
Yes, it's coming up.
Okay. Can you see the screen?
From my hand, is coming up. He said, yeah, start. Yes.
Okay.
We can see.
So we'll be looking at introduction to machine learning. We talked briefly about supervised and unsupervised learning. We talk about machine learning samples, model assessment in machine learning, logistic, discriminant analysis, the k-nearest neighborhood. Because of time, we may not be able to cover that. So we need to talk about what machine learning is all about. Is all about teaching our computer system how to make accurate predictions when fed with data. So we can see that this process is needful to ensure that our computer make accurate predictions. Now, we have two types of machine learning, supervised and unsupervised learning. And in the case of supervised learning, we have our dependent variable and independent variable. And example of such is logistic regression, linear regression, the general additive model, the lasso, the ridge. Those ones are regularized, they are penalized regression, then the support vectors machine. Those one falls on the class of supervised learning. Then in the area of unsupervised learning, we have in that supervised learning, there's no variable is important than the other. All the variables are equally important. So, and that is an example of that is a principal component analysis. In that PCA, we try to get reduced the dimension, to reduce the dimension. Then the clustering analysis, another aspect of unsupervised learning. Now, what cluster analysis does, it does to look for similarities in the categories provided. Now, let's look at the sample that we consider in machine learning. The first one is a training set. The training set usually used to train our system to train our model. Then we have the validation sample. And this sample helps to tune the model. Then after the model has been tuned appropriately with minimal error, then we subject it to the test sample. And that test sample actually, it models ability to predict well on new data. That is, it helps to identify how the model will predict well when fed with new data. And the training, like has been provided here, it is ensemble. It's known as ensemble prediction, or we can say forecast. Whereas the validation and the test, they are referred to as out of sample. Ensemble means within the sample provided, the seen data. The out of sample what is an unseen data. And in most cases, the in-sample data prediction is usually with minimal error as compared to the out of sample in most cases. So, and we have been able to identify the ones that are in sample and out of sample. Now, like we know, the set of label training data, we are at the target variable. When we look at a label training data now, those and our variable Y is unknown. Are you getting it? So validation sample is used to compare various solutions and tune the selected model, like I've mentioned earlier. The test sample is held aside to confirm how much power does the model have, the predictive power it has. That is what we use our test sample to do. Now let's look at model assessment. We have a concept called overfitting. What is overfitting? Overfitting is a case where we have low training mean square error. That is low training error and high testing error. We can equally use bias variance approach to define overfitting. When we have low bias, high variance. Low bias is associated with training sets, and variance is associated with testing sets. Now, if we have a case where we have low bias, 1% as provided here, and by the time we subject to the testing set, it gives us a high variance. So we can see that that one is actually overfitting because it's actually misleading. The training set tells you this thing has minimal error. Whereas when you subject it to what? To a testing data, it gives you high. So that is an example of overfitting. And as I've put there, oversized suit. You can imagine how somebody that's supposed to wear a suit of 40 is wearing 56. Obviously, people will laugh at him on the road. Now, underfitting. Underfitting is the case where you have high bias, high variance. And I use undersized suit. In the high bias, high variance, or we can say high training error and high testing error. Now, what's the ID model like? ID model has low bias, low variance. That is low training error, low testing error as provided there. Now, you may want to consider how to use plot to describe this. Now, we can see our underfitted high bias error. You can see what it looks like. Then the high variance error, we can see what it looks like. Then you can see that most of our point in the middle one is a good fit. Most of the points lies around that line. So it's a good fit, a better fit compared to the one with high bias error. So, and there are various ways we can also illustrate that. Now let's look at method of assessing overfitting in supervised learning machine. We are talking about cross-validation now. In order to prevent algorithm from getting too complicated during selection and training, it is important that we... Hello?
Before you go, please,
yes.
I think, can you help us go over the overfitting and underfitting again. That
Okay.
section, please.
Okay, overfitting. Now, assuming you have, when you have your data set, you set training set, you define training set, then you define testing set. If you have 1,000 data points, for instance, you may decide to say, okay, I want to use 60% for my training, while I use 40% for testing. So the first thing you're going to do is, assuming you want to do a linear regression, you model your linear regression, you now say data is equal to, because you must have defined what your training set is, 1 to 600. After it has been defined with your code, just okay, data is equal to train or training. You obtain your error there. That is your what? That's where you obtain training error. Now we are now going to, and you understand, we are now going to subject the remaining data points to testing. So, and whatever you obtain there, whatever error you obtain there is what? Is testing error. And usually the testing is obtained given the training set. So now when you now have low training error and you have high testing error, that is overfitting. That is a case of overfitting. And to avoid overfitting, there's something that can be done. It is by injecting bias into the data. Injecting bias implies you penalize. Penalizing the model reduces the variance, but increases bias. Now that is the concept of overfitting. Underfitting, on the other hand, you are going to have, for your training set, you are going to have high variance, high bias, and equally have high variance. Now, our ideal model is low bias, low variance, as the case may be. Can I proceed, or does anyone have any question?
So what determine, is there any principle that determine 60 to 40% that we are sharing, or you can, depending on the data points you are working with? For example, if I'm working with pharmaceutical clinical trial now, okay, I have a clinical trial data set. So what determine the amount I will divide for training sets and testing sets? Thank you.
Okay. Well, there's no rule per se to determine that sets the training set, that used to determine the training set and testing set. But usually the training set is usually higher than the testing. The training set is usually higher. It can even take 90% of the data. So is the researcher that will, or the analyst that will determine the training set. And you can do 50-50. Can I proceed?
Yes, sir. Thank you.
Okay. All right. So cross-validation is a technique for evaluating a machine learning model by training several machine learning models on subset of the available input data and evaluating them on the complementary subset of the data. Let's now look at, we have different types of cross-validation. Number one, the first one we're going to be talking about is k-fold cross-validation. Now we have hold out method, which was the one I mentioned that you set certain percentage apart. That one is hold out method. In that one is prone to bias because not all the data sets were involved in the training process. So now we have k-fold cross-validation. assuming we have 1,000 data points, and we now choose to use our K to be 5, that is 5-fold. That means each of them we have 200. Each fold we have 200. So the procedure is as described here. You are going to train on the four folds and test on one of the fold. That is, you are going to train on 80% and test on 20%. Okay, so now in the next iteration, you leave the first fold, go to the second fold. You are going to train on the second one. On the third, in the third iteration, train on the third one till you get to the last point. So by this approach, this is less bias prone because all the data points or every data point there is subjected to cross-validation. Now, and for each procedure has its own error. Then you sum the error. That what gives you what? The error associated with the cross-validation. It's called cross-validation error. Now, let me proceed and move to the next example type of cross-validation. Leave out one cross-validation. In leave out one cross-validation, assuming we have 1,000 data points, as mentioned earlier, what we do is we test on one and train on 999. The first iteration, the second iteration, we go to the next one till we get to 1,000. This procedure is computationally expensive, but is the most reliable cross-validation. So now I've talked about this earlier on how to reduce variance by adding regularization. And as we know, one of those of us that are statistician or we did statistical inference, a model that has less variance is more efficient. The estimator is more efficient. So in that case, as we seek, just like medicine now, the medicine will say you are curing malaria, but they will give you side effects. They can tell you stomach problem, nuances, all those kind of things. So as much as we are trying to reduce variance, we are also increasing bias. So now let's now go to classification. If there's no question, I can proceed to classification prompt. Now we have the last class, last facilitator taught us that did machine learning thought about regression.
Sorry,
now,
sir.
But here we are moving to classification because we don't have to repeat that.
They have a question here.
Yes, please.
Yes, Abubakar, please speak up.
Hello, good evening.
You are welcome, sir.
Hello.
I can hear you.
Okay. So my question is, what is the major difference between the leave one out cross-validation and the K-fold cross-validation?
Leave out one. Leave out one.
Yeah.
Okay. In K-fold cross-validation, you predetermine the number of fold you want to use. You can decide to use 10-fold. You can decide to use 5-fold. If you use 10-fold and you have 1,000 data points, what that means is that you're going to have 100 partitions. And you'll be testing on one partition while you train on the remaining partition. So in the case of cross-validation, in the case of cross-validation, in the case of leave out one cross-validation, you only test on one, while you train on the other data points. So the difference is that in K-fold, you have fold, number of fold you are considering. In leave out one cross-validation is only one you leave out. while the rest will be trained. And the testing will be based on only one data point. Is that clear?
Okay, thank you very much. Yeah, thank you very much.
Okay, you're welcome. Now, in supervised learning, I think.
Sorry, any other question again before we move to the, yes, somebody is typing. Okay, it's the same person. Okay, but are we saying, Dr. Adeshina, are we saying that yes, the best way to test for cross-validation is between K-fold and leave out one?
Yes,
method?
Yes.
Okay.
It has been proven to be more reliable.
More reliable. Okay. Over to you, sir.
Okay. Now, hey, okay. What am I doing? All right. This thing is hanging.
Classification. Well,
okay. Now, classification is very, we have supervised learning is very into two, regression and classification. We know that classification is used to predict qualitative responses, maybe like low, medium, high, something like that. It's qualitative, and usually qualitative in nature. Now, and we know that the classifier that are applicable to qualitative data is logistic, linear discriminant analysis, and k-nearest neighbors. So these helps to fit classifier, or we can say classified data. Now let's look at logistic, which you all know. The model in equation 1 here talks about when we have just a simple case. Equation 2 is when we have multi-class, multi-case, and we have equation 3 to be our odd ratio. And you see the logistic cannot be modeled using OLS. It's usually maximum likelihood approach and the Newton-Raphson method. And you know why? You know when you fit OLS, you can't get AIC, all those criteria, because they are not likelihood based. But when we look at logistic regression, you can get your log likelihood, the AIC, BIC, and what have you. Now, in the case of multi-class response, this thing is okay. Multi-class response, linear discriminant analysis is more robust for fitting classification problem for responses greater than 2. Okay, and we know that logistic regression is not so popular when you are considering multi-class case. And the reasons why discriminant analysis is preferred to logistic regression have been highlighted below. Is more stable than the logistic regression. Then, talking about the discriminant analysis, in doing that, we employ the Bayes theorem, and as we can see in our equation 4, we also have that in equation, I can see equation 5. Equation 6 is telling us that a case where, that is for when our predictor is equal to 1, it's talking about a case where, assuming we have fail and pass and fail. So this one can handle it conveniently. That equation 6, talking about the summation, we know what Bayes' theorem is all about, and that is represented in equation 6. Now, in the case where we have linear analysis of greater than 1, that is when we use, we talk about multivariate Gaussian density. That one is applicable for when predictor is greater than 1, that is, then is expressed as follows. This is the mathematics behind it, where our X is normally distributed with mean, and our gamma is our the variance representing the gamma, the variance part. And the covariance is expressed as that. Is a matrix, actually. Is a P by P matrix, which is the square matrix. And also the classifier is also further defined. We also talk about the quadratic discriminant analysis, which our observation is taken from X normally distributed mu, mean data, and K for our variance, our class. So to leave all the statistics related or mathematics, let's go to the practical aspects, which this Zoom is. To practicalize what I've been saying, we are going to be using a data set called S market, at least stalled markets. So S market. The data of this that we're talking about here consists of 500 stock index over 1,250 days from 2001 to 2005. And we can see that this data set is built into a package called ISLR. So that is, if you install this package, if you have not installed this package, kindly install this package. This package, kindly install it. I hope you have been taught how to install package. Go to your House Studio and install ISLR package. I think I have to wait until that is done, but I think this is one of the packages that comes with the software, if I'm not mistaken. This package usually comes with the software, the like of mass and this one, but kindly check if you have it in your library. Check your library if you have ISLR package. And if you have it, kindly go to your chat box and say yes, so that I can know whether to proceed or to hold on. While you do the installation. I can't even see the chat. Okay. Have you checked if you have the package in your library? Dr. Okay.
Yes, sir. One thing I'm just trying to put the what do we call it now, the how, but they have the data set is already on the platform.
So okay, they need the script.
The script, yes. So I'm just looking for the script, trying to download it to my phone because I can't attach directly. I don't know why it's not agreed to attach directly with the Zoom.
Okay, maybe on the WhatsApp group, they should be able to access it from there.
I believe you've downloaded the data and the slide. So just hold on while we are trying to upload the R script. Or is it possible you can upload the R script from your site, sir?
Okay, let me try.
Just try if you can upload it. I don't know why.
I don't even know where attach is here.
It's there.
Attach. I can't find it.
You can't find the attach there.
Attach is not here. I can see emoji. I can see format.
Or can you send it to the Zoom?
Okay, to the Zoom. Okay.
No, to the, sorry.
What, to the platform?
To the platform.
Okay. Okay, I'll do just that.
So you can understand now. Just try if you can share it on your screen on the WhatsApp so that people can download it.
I forwarded it to the group. I hope.
Okay.
I hope it will open, because like you said, you encounter problem with it. Okay, so let's see.
How many of us can download it, please?
Well, I think they have to first send it to their mail. WhatsApp may not, if they don't have the app on their WhatsApp, they may not be able to access it.
No, not assessment, as in just forward it to the Zoom, to the system.
It's on the WhatsApp. It's WhatsApp. If they have WhatsApp on the system, they can access it from there. But if not,
from there, that's true. You're right.
But if not, maybe they may have to forward it to their mail and open from their system. Okay. Okay, let me be talking about the data while we are doing other things. Now the data is about, talks about, it has 9 variables. 9 variables. Variable number 1 is the year, lag 1, lag 2, up to lag 5. Then volume, number of shares traded on the previous day in billions. Today, another variable called today is percentage return on the date in question. Then direction, whether the market goes up or comes down on a particular day. Now, this lag here, lag 1 means the sale given yesterday. That is, when you talk about lag, talk about current day, right? Okay. Now, when we have, let's say we have S now, S of T. S of T is today's sales. Now, yesterday is what? S of T minus 1. For lag 2, T minus 2. Lag 3, T minus. So that is how the lag works. Now, the volume of share, then we talk about today, percentage of on the date in question, the direction, whether it goes up or down on that particular day. So we might have to come back to, since I'll still run through the slide. The codes are here. Then you also have the code on the higher markdown, the script. So while we run through the code here, as well as trying to access the other one. Now, to do that, we call the package required. And inside this package, we have the data called S market. S market, when we say edge, like we have been taught previously, it produces these first 6 observations. The dimension here gives us the dimension that is 1250 by 6, by, is it 9? Okay, by 9. Then you want to plot and see what it looks like. You just put your plots, S market, this $ volume. That is, there are other variables in that S market. We want to pick volume, and that's why we use this $. We can say square bracket, comma, probably maybe it's the 7th variable. Then we can choose our color. Color can be yellow, can be pink, can be whatever color we want. Then our plot to be produced. We are going to do that in practical. Then the correlation S market. Now here we want to obtain the correlation of our stock market. Now if we do this correlation, it will not produce. Why? Because it has the direction is not actually numeric. That is why it will give us error. See, it contains non-numeric. So what we do next is what? We just exclude variable 9. That's why we are saying correlation subject to after removing the 9th column. So we obtain our correlation matrix, 8 by 8 matrix. Okay. Now we assess the outputs. Now down to logistic regression. In logistic regression, we have to use our generalized linear model, unlike the OLS, the linear regression. Linear regression to fit linear regression, the function is LM. But for logistic regression, the function that is applicable is GLM. And we also declare our family to be binomial. If we declare the family to be binomial, it's obviously going to fit logistic regression. Then the next line here, we have summary. Because we have declared GLM fits to be the model, right? It could be anything. You can just say ordinary fits. But what you need for the summary of is the GLM.fits. Then we obtain our GLM.fits, our coefficient, that is the ordinary coefficient. We want to just look at the coefficient only, not minding the entire summary. In the summary, you are going to have your standard error, you are going to have your p-value, you are going to have t-value, but here, just what you're interested in is what is just the coefficient. Here now, we talk about summary, GLM.fits, considering only 3 coefficients. That's why we have comma, square brackets, comma 3. It produces coefficient for only 3. Now, the next thing we want to do is to predict now. To predict whether our stock market goes up in a given day. That's the probability we want to obtain now. To do that, we are going to say, we are going to use the function predict. We put our here, we have not started using the, we are not using the training set and testing set yet. But this one we are doing here, what we are just doing here is just using the entire data as training, at the same time using that was as testing for this particular one. We are going to move to where we use training set and testing sets particularly. Now, in this, we have been able to, this particular line, the next line that says GLM.props 1 to 8 means instead of, you know, the probability will give us 1,250 values because we are predicting for each day prediction. So, but we are not interested in knowing what each day gives. We're interested in first 8, 1 to 8. So we just say, okay, GLM.props square bracket 1 to 8. If you're interested in 7 to 25, just say 7 full column 25. It will produce that. Now the construct here is just telling us that, okay, What is the construct? S market $ direction. So what is the only thing we need there is what? Is 0 and 1, binary. That is what the construct means. Now we want to determine whether the market will go up or down on a particular day. What we do is just, okay, we want to replicate. This function as seen here is replicate down. That is 1250 times, you know. Now I want to now predict now. Predict glm.predict now, dot spread, right? Now we now say glm.probability greater than 0.5. That is, we have the probability of 0.5 that it will go up on a particular day. Now we now form our table. Table, open a bracket, glm.pre-direction. This table that it will produce is called confusion matrix. Right. It's called confusion matrix. Now you can see that this one was done twice. Without the S market there, it's not likely going to produce anything. Say you say it cannot see, the direction is not found. But we have to subject it to that particular data where you can find direction. So we can see that it will give us our confusion matrix, because we are going to, when we go to the main script, when our R studio is open, we are just going to be running it line by line. There will not be time to explain each step in details. So we now look at our mean, the fraction for whether true or false. Now you can remember that the last, I think, second R lecture, we had thought about Boolean, the Boolean, talking about true or false, double equality. Okay, so that is what it actually stands for. Okay, now let's look at, now if you look at it critically, the data set we are given, the data set is basically from that package that we ISLR. But now, should you be interested in this data set, what you just need to do, you have to write it. Writing this data set means you are going to export the data such that you can use it without referring to this the package. What you do, the command is what? Write.csv. If it's XLS you want, you put write.xls. Then what's data? S market file. You name your file. That's why I name it smk.csv. That's for Excel. Oh, there's a mistake. Now for SPSS, it is. Please take note. When we get there, we'll do it. Is SAV, not CSV. The SPSS is .SAV. That's the only difference between exporting in SPSS and exporting in Excel. Now, after we have obtained the data, you're already aware, you already know how to import data into the R environment. We can now use this command to do it. This is my own, what is it called? My own, what is it called? Directory, okay? Now, this is my home part. So your home part will be different from that. Just give an example of where, assuming, and that's why the data set itself, after I exported it, I now sent it to you. I got it from R. So should you want to go through the route of installing or importing your data, you can equally follow that path. But the data is already available in R. And if you look at it critically, if you now use this one that you have imported directly, you will notice that there's up and down there in the direction. But the second one here, the last part here, you have to recode it where one is what? Represent up, is 0 represent down. And you can simply do that in Excel by saying find. When you find and replace all, anytime you see UP, you change, replace with 1. Anywhere you see down, you replace with 0. So That's what I did, and I save it as S market 1. So that when you get to where you will need the binary, you will not be denied. That is why I have the two variations. Now, let's now go to the logistic training and testing. Now, for the training, we have S markets for the year less than 2005. They are the training set, that is 2001 to 2004. They are the training observation, and it contains 1 to 998. These are the observations, and we set them to true. Now, looking at the S market train, you can see it's just a replica of what we have there. Then for our tests, S market, when you see the exclamation mark, actually is a reverse Boolean. So which means the reverse of what we have, 1 to 998, it will now take what? It will now take 999 to 1250. When we look at the dimension, it will give a dimension. Then the direction 2005 is equal to S market, this then train. So this is what has been done. And when you look at this direction, it's actually the dependent variable that we are trying to predict. So we now go to our logistic regression. Now, the previous one, we did not use the training set, and the training set separates the tests. Don't forget that I said earlier here, I said when you use, in this case, the entire data was used as training and testing, but here we have subjected it to the training now. So we have our subset, we have our data already as our S market. Then we have our what? Our subset as train. So what we now do is, when we fit this one, it gives us something, and when we find the summary, we'll be able to obtain the result, which is a replica of what we have in OLS when we fit our linear regression model. Now, we want to compare actual movement now. So what we are now trying to do is to replicating 252 for down. So on our GLM.predict, we have probability of it that it goes up 50% of all the cases that, okay, if it goes up. Now, in that case now, we now produce our confusion matrix. So we now find about the mean, we obtain that. When we get there, we'll see how this works. Now, okay. So logistic regression with variables. Oh, there's a mistake here anyway. All right, now let's look at after fitting the model, we discovered that some of them have IP value. So when you have IP value, we now decide to go for the ones that have low P value to see how the model will perform. And that is what we only repeated. We are repeating this step only with 2 variables. So, and that is what we have here. Everything here is cost. Now we go to linear discriminant analysis. In doing that, we need package mass, which usually come with R. We don't need to install this, usually come with R. It comes directly with one of the libraries provided. So we now subject it to this linear discriminant analysis, and we obtain that. And after that, we predict. We conduct our prediction. We conduct our prediction, and we follow the procedure. Okay. Now, at the end of this place too, we will obtain our confusion matrix, and based on the confusion matrix, we'll be able to determine if the predictive power of the model and able to tell how strong our model is in predicting the rising or falling of the stock in a given day. Now, the last one we are talking about here is what is quadratic discriminant analysis. And we have still relying on two variables as independent, the lag 1 and lag 2. Okay, then we can see our subset is trained. Then we fit that. We are going to obtain our fit. Okay, and our fit is a replica of we are going to obtain something like the coefficient. The coefficient. Then we now predict. This function helps us to determine the accuracy of our model. So before I proceed to the lab session, let me assume that we all have you have sorted out the R script.
I believe so. Even if you cannot, for those of us that cannot download the one on the platform, you can easily copy the one on the slide and it will also work.
Yes, that's fine. So you open your R Studio, you just copy and paste. It will produce the same thing. That is why the scripts have been made. So now let's look at the lab, the procedure now. Now, the first thing we are going to do is to call the package required. Then I run it. When you highlight this and run, the R environment will recognize it. Okay. Now, should you want to know what the data looks like, then we can go to the next slide and look at okay, the data I want to work with. How does it look like? Then we can see.
You are not sharing your R. We are still with the slide.
Okay, let me try and do that. Okay, all right. Okay.
Yes.
All right. So what I've just done here is, for the sake of some of us that are new, now you have the what was it called? This R Studio. I light this, okay. Then I run. If I do this, you can look at the run here. It registers this package into the environment. It brings it up. Now, the next thing is, okay, we want to check. We also go and run this. We also check what our variables look like. You can see that for 2001, that particular day, 2001, because it's every day of 2001, 200% day 1, day 2, like that. The lag is what? Is 0.381. You can see that for today is what? 0.95, 0.959. So that's for today. Now, we want to look at the dimension, because if we are to produce all these 125, it might take the whole space. Let's look at the dimension so I can have an idea of what is 1250 with 9 variables. Okay. Then the summary. We want to look at the summary statistics. We also click on live that and run. We can see what it looks like. Our mean median, first quartile, second quartile. And if you're interested in variance, it's just a matter of saying variance this. But you have to be specific of which variance you're looking for. So, okay. Now, let's plot. Here, I have red here, right? Okay. I have red here, but I may decide to use blue. Okay, I now change it to blue. I can plot now. I've plotted a blue figure that describes not for all. You can see that, you can see the dollar sign there, volume. Okay. And if you don't want to use this dollar sign, you can just say S market, square bracket, what 1, 2, 3, 4, 5. I think 5, I think will give us the volume, or 6. Okay. Yes, just a square bracket 6 will produce the plot for volume. Now, the next thing we need to do, we can also check our correlation. Now, let me run this. Now, trying to check correlation. Like I said earlier, there's non-numeric stuff there, which is the 9th variable. So in order not to have error here, what I need to do is the next line, it is -9. So that one exclude the 9th variable, which is non-numeric. Direction up and down. So what I do now is I can now run this. You can see the 8x8 matrix now. I think, yes. So now we will look at it critically. You will see that they all have low relationship, low, are you getting me? Low relationship, low correlation coefficient, except for year and volume.
How do you determine low relationship? Is it because of negative and the positive? Dr. Adeshina.
I think it's having a network matter.
Yeah, I can hear. You're welcome, Mr. Musoya. You're welcome, sir. While we're waiting for our facilitator, you want to say something?
Yes, I just want to quickly respond to a question that somebody just you have a very low when the value is less than 0. When it is small, whether it is a negative small or positively small. The negative and the positive shows the directions of the correlation. But the value, how small the value is, shows that it is not, there's no correlation between. So if it is going towards 0.1 above, okay, we can begin to believe that something is small, stylishly happening. But when it is 0.4, we call it a mild correlation. When it is above 7, we say there's a strong relationship. Okay, whether it is a negative or a positive, but the value is what matters most. So when it is very small, 0.0 something, we declare it as a there's no relationship that is actually existing between those two variables. Okay. And the test is very essential when you are looking at the independent variables, so that we know that there is no relationship with the independent variable. Because if there are relationships between independent variables, it means that there will be a conflict in the response variable because there is already multicollinearity existing in your data set. So there will be need for us to treat it. That's why the concept of correlations will be also needed to check if those independent variables are also related.
Ogusoya, please lower the volume of your TV set.
Okay, sorry, sir.
The background we can't hear very well.
Yeah,
thank you, sir. Can you please repeat that particular last part you're saying about
I think it's better. Is it okay now? Okay, so what I just said is just that for the correlation, one of the purpose why we need to do correlation test is to see, most especially the independent variable, if there's any relationship between them. So, but if you discover that there is a relationship which also talks about which shows that there is a relationship, if one of the independent variable is influencing the other, okay, so that means that we need to treat it. It's either we subject it to further tests or remove one or do some manipulations on that data set to make it non-related. Okay, so, and that's why we need to find that correlation. So correlation is also determined when zero something, we declare it as a small, so it's approximately zero. So most times we use 1 decimal places. So when it is 0.0 something, we declare it small. So, but when it is beginning to have maybe 2, we say 3 is mild. So when it is 4, it is averagely okay. But when it's going to 7, we say 7, 8, 9, it's a strong relationship that is existing, and which is very dangerous for independent variable. But for dependent and independent variable, it's okay. Okay, because that's exactly what we're interested at. So when the value is actually small, the sign shows the directions of the relationship. Whether it's a positive, it means that they have a direct relationship. But when it's a negative, mathematically we say it is indirect relationship. So the increase of 1 unit is causing a negative effect to the second one. So that's what is those effects is saying.
Yeah, thank you so much for the input. While we are waiting for our facilitator to share his screen, over to you, Dr. Adeshina. So please, if you have any question, kindly put it on the chat. If you want him to explain 1 or 2 areas that is not clear, please put it on the chat. Please unmute yourself, sir. We are still, I think he's still trying to struggle with the network. Ogusoya.
Do you have the slide there?
Yes, that was what I was trying to.
Fortunately, I'm using my phone where I am. I'm on a
No,
transit.
I actually have the what do we call it? The slide and the code. Let me just share my screen while we're waiting for him to join, because of our time. I see the screen. Okay, somebody asked a question. He said, if the correlation coefficient is very low in linear regression, for example, 0.1, is there a way we can improve on it like Ogunsoya.
He's talking about, is this talking about the explanatory variable and the response variable? You don't need to respond, it just give you the true nature of what you have. So it's just like you and your wife, and the test is carried out, and the test revealed that the relationship is very low. What do we do to it? Okay, so it is the data. As at that time,
you spend more money so that the relationship can be solid. That's
okay,
amendment.
So,
is that no amendment? Somebody asked for amendment. You said you will keep it. Okay, sorry.
And the money can be outlier.
Okay, the money can be what?
Outlier. Yes.
Oh, which money outlier? The woman will be happy when you said outlier is even their player. Over to you.
But the point is that data itself cannot be changed except you now improve on the next data that you're likely, or your relationship with the wife. Okay, but the last relationship that we have measured, it shows that there is a low one. So nothing you can do to the previous one. Now, but it's an indication to tell you that, oh, I need to improve on what I have. Then it is now, if it is the money that is making the relationship not to work, then you ingest money, which is your coefficient, the coefficient of the explanatory variable. For example, the man is the explanatory variable in a relationship of marriage, while the woman is the response, is just responding, collecting, receiving. So what you do to her will depend on how the relationship, because we know that it's the woman that owns the family relationship. So whatever you do in that relationship, where you, husband is the explanatory variable, and the coefficient there is your effect. For everything you do, it shows that that coefficient is the value of your contribution to that response variable. So that is the model that you have designed for us. But if you don't want to improve on the model, then you begin to work on, I gave 5 naira before, let me change it to 10 naira. You will see that the model will be improved. Thank you, sir.
Okay.
But, sir, in addition to what you are trying to say, I think the question is there that if there is a weak correlation, another model, the model you are considering is a simple linear regression model. And there can be a strong relationship between those two variables if you try other models, which are not simple linear. It can be non-linear. So it's not only the fact that maybe a linear, it can be telling you that that model you have developed is not even good to capture such scenario. So you can look at other models too. So I think that's another thing they can do.
Thank you, sir. Let me ask Dr. Olumide, do you want me to share the screen for you? You can just talk.
Hello?
Hello, can you hear me?
Yes, I can.
So is it possible we share the code from my end so that you can just explain?
Hello?
Hello, sir.
Please come again.
I said, can I share this?
Hello, please come again.
Can I share your slide while you just explain?
Yes, share from your end and let me explain. Share
Okay.
from your hand. I can't share my screen because I'm
don't
using my
worry,
phone.
we'll do that.
The system is not connected due to network.
Yes,
please.
I'm sharing right away now. Can you see the code? Can you see it?
Yes, I can see it.
Okay, good. So we are in line 8. Go ahead.
So line 8. Kindly help me, kindly run it so that I'll proceed from there.
Okay. Over to you.
Okay. Yes, we can see that. Oh, please, let me bring it down a bit. We can see the results here that, to all the variables showing the output, all the. Now we can see that all these, the p-value here shows that they are not, the p-values are large. The p probability, they are large, which actually suggests, ideally, we would say they are not significant at 5%, or even at 10%, they are not significant, right? So, they are not significant here does not mean that there is no relationship, but the relationship exists, but is not significant. Now, there's difference between 2.1 and 2.0. But the difference is not much. But that's why we can see that, okay, as you are predicting the direction, whether rise and fall of stock market in a particular day, using these variables to determine what impact on the stock market's rise and fall. Looking at these variables, they are not significant. The p-values are large. However, it doesn't mean that when you look at the lag 1 and lag 2, those two happen to be the ones that have the least p-value. So due to that, we can retain them and see how our model will perform. We can see this 0.145, 0.398. Now, let's, as some of you that are familiar with stepwise regression, forward pass and backward pass. This one is what? It's backward, because we are removing 3 out of the variables. We'll be left with only lag 1 and lag 2. However, before we do that, let's run the next line. What is that, please?
So we've done a summary, and no, we've done a coefficient. Now we are in coefficient now.
Okay,
line 12.
Coefficient, yes. Coefficient, we can just see the coefficients of just the coefficients.
Yeah.
Removing all those other dispersion parameter, all those deviance, those ones will not be there. Good. I think I'm back online now. Okay. Oh, the thing has disappeared again. Child. It's just disappearing and appearing. It's not okay. Now you have gotten the coefficient. Now the next line is
summary of coefficients.
Summary. Yes.
This is summary of coefficients.
Okay. Yes, the next line. Considering 3.
Yes.
Square bracket 3.
Yes, I've done that.
Okay. All right. I can't even. Okay, I've seen it. Yes, I've seen it. All right. Then let's now go to, we want to see the probability of obtaining of our stock market going up. So, and that is what is next now. And that's in line 16. Probability of stock market going up. Okay.
What do you mean by?
I said, mommy.
Yes.
Have we?
Yes, we are there.
Okay. 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 Now, if you look at that result, this will produce 1,250 probabilities for each day. But we are interested in only first 8. You can say, okay, 1 to 100, but this produce first 8 probabilities. So I did only on day 1, probability of the stock market going up on day 1 is what? 0.5079. The following day, 0.481, like that. So that is what that gives us. Now let's look at probability of on the particular up. Let's now look at that probability now. Before we do that, we are going to replicate the okay. So whether it's going up or down, we have our code in line 20 and 21. From there, we now plot matrix, or you can say table. You can see from line 20 to 22. You can see, okay. This network is not doing well.
So
Okay.
we understand the network issue.
Now, this is telling us that there's no object called direction, Abi.
Yes.
Now we can now see that if you don't acknowledge the S market, because it's inside S market, so that's why we're able to now produce the confusion table now, or the matrix. So we can now see probability of going up, we can see, and down, we can see what the matrix look like. Now, we want to obtain our error rate now. We want to obtain our error rate.
So we have it.
Now, how do we obtain that? Now we have our, of going up, we have 457 and 507. Then we just add it up, divided by the total number, which is 1250. The same thing by saying mean the line 24 and 25 should be the same thing. And you can, if you do line 24, it is the same thing as doing line 25. Is that clear?
Yes, but it's still telling us that object.
Okay, the direction. No,
yes.
So let's put the S market in front, please. Kindly put the S market $ in front so that it can actually.
You mean this place? Line what?
Yes, before the direction.
Yes, before, okay, after the S market, before the X market $.
After the equality.
We are on the table, please. Is it line 23 or line 22?
Okay. Now, I'm actually online, but the line is not stable. So
just do it on your laptop without sharing it.
Line 23, yes.
Okay.
No, line 25. It's not what I is telling you that it's not object directions not found?
Yes.
So line 25, you now put, just like you replicate what's in line 23 in line 25, so that
are you saying this? Can you see my line 25? Yeah. Can you see it? I think we lost him. So I think we lost him because of the network issues. So at this point, what he's trying to do, we are trying to find he said error rate, and we've calculated the error rate. We have the error rate, and we're using another method to also calculate the error rate using the. Are you there, then, sir? Okay, over to you.
I'm there, it's not stable.
And so we've done the line 25. We have the same answer now.
I can't. Hey, this thing is not. It's not stable. It's not stable. Are you still sharing?
Do you want me to stop sharing?
Okay.
Is this saying that?
What's it saying?
So we have the answer already.
We can't.
0.52.
Okay. Your skin is not visible again.
No, continue, please. Continue sharing, but I can't see it.
I can't see it too.
So
bring it up again, sir.
Can you see it now?
It's not, yes. But because me, I'm using phone.
Can you see my screen now?
Yes, I can see it.
Dr. Adeshina, can you see my screen?
You can double click, you can open, you can expand it to see it clearly.
Yes. I don't know if
you
can expand your screen from your phone, it become bigger so that I can see it clearly.
Can you all see it now, Ekum?
Yes, we can see it.
Okay.
Can I speak to this confusion matrix?
Go ahead. Let's go ahead from 23.
What
20? Where we had that. You can go ahead from there.
Okay, where you are, or where the DLM predicts as against this, that's confusion matrix. Okay, which talks about the true positive and the true negative, while we have the false negative and false positive. Okay, which means that we are trying to look at the error committed by our prediction in relation to probably success or failure. There are different measurements. Okay, if you allow me to just make a revision of some of the things that Ekum has. We have what is called accuracy. We have the F1 and recall. Okay, what it does is it measures how perfect you are, while the recall measure what is the level of error you made and compare with your success. Okay, so but what I see here is we are trying to look at the level of our error based on this analysis. Okay, so what you see here, where you have the 507 plus 145. Okay, so that is 507 is the false negative. Okay, that means you have negative, wrong predictions of negative. And as against correct predictions, true positive 145 over the total, which actually measures what the level of accuracy. That's what accuracy measures. All right, so we have seen that our accuracy level is defined to be 52% for the trained data set. Is it the trained data set? Because I can't see it well.
No. with the train and the text. So we have the two together. We have the
Okay, so we have the test now. Okay, the test error rates of the train and test data. Okay.
Hello, sir. Hello, sir. For you to see it, you just expand your screen from your phone. Since you are using phone, it's expandable from your phone. Expand it, you see it clearly. Just expand your phone. Just click on and touch your phone screen and expand it.
I'm closing it. I don't know what's up. Some part of it is closing.
Yes, thank you.
Okay, it's back.
I can see.
My own is closing up here.
Okay, go ahead, sir.
Yes, I'll rely on this your screen. Yes, so this particular line is telling us that, like I said, initially we didn't set aside training data and testing data. So for this particular one now, what it's saying is that the prediction was based on the entire data set as training at the same time as testing. As Dr. Soya just said, the error rate has been false positive and false negative over the entire thing. We have 52.2%, which actually is not good. It's not a good rate. So we further need to look for other measures to see, to have a better testing rate, testing error rates. Now, before we proceed, I mentioned something about writing, exporting data from this environment. If we do this particular line 28, if you copy and paste line 28 there, it's because the data we are using is from R itself. So we should want to have this data set and use some other time for something else, even outside the environment of R, we can just write. So kindly help us write this. This will not really work because just help us run it. I'll tell you the reason now.
Which of them? Line 28?
No, line 28.
Okay.
Line 28.
It's work.
What did it give you? Okay, now the reason why it's initially I put it as SMC. Yes, it's working because it is not from your system. Now, if you look at your document, go to your documents and search SMK. It will give you this particular data set in Excel format.
Oh, okay.
The way the data is in Excel, you will obtain it like that.
So
now,
is it okay?
No. What?
Is it okay like this? We should continue.
It's okay. I can see it. It's okay. Now I'm using the system now, not my phone. It's very
okay.
clear.
Should I stop sharing?
You said no. Continue sharing, please, because the thing might go off again.
Okay.
Now,
go ahead.
If you now go that same SAV will give you SPSS. So that CSV on the second one was a mistake. So put SAV there so that you can.
You mean this side SAP?
You can obtain it. No, line 29.
Yes, line 29 instead of CSV.
CSV, yes. SAV.
SAP, okay.
Yes, it gives us SAV, V, not P. V. V for violin. Okay. So let's run that. That will give us our data in form of SPSS.
Okay.
Okay, if you go to your documents, you go to just search again. When you see SAV, if you open it, it's SPSS that you open for you. Now let's now go to the training setting aside the training and testing data now. Now, line 32, I think I've already explained this in the slide. This is just to run it. So we may not dwell much on this. So you see that that produce line 32 produce the training sets. That's 2001, 2004, excluding 2005. And that gives us 998 observation. Then the next line also is a replica of, the next line is a replica of line 33 is a replica of line 32. Oh, is the dimension. Wait, okay, that's line 35. Line 35 is the dimension. Have you run line 33?
Yes.
Market train
is here.
Okay, thank you. So now our direction 2005, like we said, we only consider 2005, and the direction there is for our dependent variable. You can see that you also see that that's exclamation actually negates the train. So by implication, it's actually test. It's work for the test data. Now let's now go to the logistic feeds. Now, as we did before, there's nothing different from what we did before. The only thing different here is that we are subsetting into train, the training set that we did before. So line 39 and the summary. Okay, I think you've done that already. Okay, and you can see the summary. Can see the summary. Okay, here we can see also that we can see that the p-value is high anyway. So let's now go to the test now. We want to predict now. We want to predict based on what has been, what you already fixed, and with our test data, we can see that what do we have? Line 41.
Yes.
Okay. I can't even see. Line 41. We have our, okay. All right. Now the next thing is to, in an attempt to obtain our confusion matrix, we go in the route, the way we did the previous one. We can now obtain our error rate here. That's the following up to line 45. Line 45, we can see. Now we want to obtain our error. Our error rate, line 46, 47. Okay, yes, we can see. This thing is actually blocking me. Okay, good. Oh. Okay. Now, what about line 47?
Yeah, it's there. Okay, line 47 is here.
Yes. Okay, now I put a note there already that line 47 also gives us 52% error rate. So you can see that the first one we did was the guess, kind of, which was without using the training and test set, without separating them, using the entire data. So we can see that this one is not much different from what you obtained, the error rate. However, we want to now use the lowest p-value, the ones that have the variable that have lowest p-value, which is lag 1 and lag 2. So let's go to line 51. Line 51, please. Line 51. Okay, and 52, we have a summary. Okay, we've done 51 and 52.
Yes.
Okay, good. So now we still also need to further proceed and check our error rates. Kindly run the following one so that we can move, because we have done all this before. So just a replica of what has been done before. Okay. Okay. So what's our error rate now?
Well, our error is there.
You can see it's very high now. It's 56. We can see the error rate 56 of daily movement. So now, as we can see, now that takes us to, we want to now assess this based on discriminant analysis. Like I said earlier, I said discriminant analysis is more stable than the logistic regression. So, and that takes us to discriminant analysis. And to do that, we need library mass. I hope we'll just try not to exceed the set time, 9 o'clock. Now, we use library mass, then we fit. In this case, we are going to be using LDA. We subset it to train, and we can see that we have our group means. We can see for lag 1, we have down, we have up minus 0.33, lag 2, we have that. Then our prior probabilities of the group, we have for down, we have 0.49, for up, we have 0.51 approximately. Now, looking at this coefficient of linear discriminants. Now, the coefficient, what it means is that if we multiply minus 0.64 times lag 1 and minus 0.513 times lag 2, if it gives us a high value, it means that the stock is going up. Otherwise, if it's the value we obtain is small, it means that the stock is going down. And we look at this, the figure that we are given here actually describe what we have for the coefficient. Okay. Now let's look at the predict now, line of 70. Line 70. Okay. All right. Okay. Now. Okay. Now, looking at this, we can see that the threshold probability, the probability of predicting accurately, we are talking about 50% now. We have a threshold to be 50. And when we look at what has been provided, let me see the thing clearly. Okay. All right. So we have our 55.9%. Okay. Is that all? Are you up to 78 now?
Yes.
Wow. Okay, we can see that the sum of the, say for we're talking about if greater or equal to 0.5, but this greater than 0.5%, that it will go up is what? 70 cases. While for it going down, for less than 0.5 is 182 cases. Okay, let's consider the quadratic discriminant analysis, and let's see. We will see that this particular one is much more. Now, line 81.
Yes.
Okay. Then the fit also, you know, just a replica of what we have in the linear. I'm talking about the output. Now look at the confusion matrix. What do we have? Okay. Now let's look at all right. Okay. Now we have now what this is telling us is that we have 0.599. What it's telling us is that the model, the prediction is 60% accurate 60% of the time. The prediction is accurate because if it tells you that there's a rise in the stock market, there's 60% assurance that it actually rise on a particular day. That is what this discriminant analysis has given us. That is what was produced here. So we have, I think we have been able to run this in your own private time. Just play around with it and see what you can obtain. So we have time for questions so that we use the remaining 10 minutes to do that. This is just an aspect because there's still, I hope next week, we are still going to look at multi-class. Multi-class where is beyond, you know, here now we are talking about up and down, rising and falling. There are cases where we have more than that. How do we handle that? And how do we predict accurately? Because there's possibility that what you have on a particular day, if your prediction also produce the same thing, it shows that your accuracy is very high. Otherwise, one need to adjust. But when we look at multi-class, we can consider that sufficiently. But this actually demonstrates the training and the testing set that was earlier explained to us, and the procedure involved in machine learning. This is just an aspect of it. We are still going to the cross-validation aspect. I just pray that the internet is stable by the time we will go for further lab sessions. So, Dr. Okay, over to you.
Thank you so much. Thank you. Let me stop sharing. Okay, do we have any question, please? Have any question for us, for the presenter today? Let's please raise up our hands before. If you enjoy the class, can you please put it on the chat? Just a thank you message, send a thank you message to our facilitator today. Please, if you really enjoy the class, and sorry for the internet glitch, as we all know our statement in Nigeria is the internet glitch or whatever we call it. So anyway, that's on the lighter mode. Can we please send a message? Let's just see our reaction on the charts. Thank you. Yes, Obiagili, thank you for that message. And whereas again, you enjoy the class, you enjoy the presentation and the time spent with our facilitator today. Thank you, Oluwaseyi, and I can see. Thank you, Sarubo Bright. Thank you for the message. So I want to use this medium to also thank our facilitator today, Dr. Adeshina. We enjoyed the presentation. I will also work on that. I want to use this medium to say thank you once again, sir, for your time, for the investment, for all the efforts just to make sure we impart the knowledge, we send the message out there, and I believe God will reward you accordingly. Amen. So do we have any questions? If you don't have any question, Are we meeting on Saturday again?